Yeah, thank you, Professor Ashok. How do I hide this bar?
Sorry?
There is some tape coming up on this one. Oh.
I think if you press Control L, maybe.
Oh, 1 second. Yeah, I think it's fine.
Yes, it's good.
Yeah, so I was taking some input from Professor Sairam about the background of the participants. And so since the participants are from different backgrounds, and the course structure does not have the introduction to neural network as such, I was thinking that before starting the sequential model, we should have a brief discussion on neural network in general, because sequential model that I'm going to discuss, neural model that I'm going to discuss is a special type of neural network. Okay? So how a neural network in general looks like and how it works, I think a brief understanding and what are the different applications, why neural network is becoming a say important model. Okay? So I thought of starting with a very basic introduction to neural network before we start with the sequential model. So first, let us try to understand why do we need to study neural network, right? So if you pick up any any problem today, right? So I think there is always an application of neural network. So if you say a classification problem, something like so classification problem basically means, say, if you say that suppose if I have a certain object, let us say I have some object here. Let us say this is an object, and I want to label, okay, what is this object about? So maybe that, I would say this is a picture of a human being. Then I want to classify this as a human. Or if I give some kind of vehicle, okay, something like a vehicle, another image or some input, I want to classify this as a vehicle. So likewise, you may have, say, many of the real world problem today belongs to a classification problem. So classification problem means, so if you have a classifier, okay, that can be built with various methods, and the neural network is one of such model that we can use for building a classifier. So if I have a classifier, and in this classifier, if I give some new input, okay, this classifier will assign a level to the input, okay, and the levels are predefined from a set of say the predefined levels. So if I say if my classifier is about human or vehicles, okay, so given an image, I want to classify is it a human or is it a vehicle? Okay, so this classifier can only perform classification of these two levels. So this is a class. You take up the classification problem. Neural network is there to can be used to perform that. So you have also seen the regression problem. I think in one of the discussion, regression problem is like given say some sequence of input or some set of input, you want to predict something in future in a real number. So neural network can be used to perform solve the regression problem. Okay. So, say for example, that given a set of say vehicle price, okay, in the past, say past 10 years, and I want to predict what might be the price of the vehicle in the next year, right? I can probably plot in the general regression. What I can do is, for different years, I can plot the data, and I can fit a curve and try to predict what might be the price of this particular duration, which is going to be this price, right? So this is a regression, right? So for a regression problem, also you can use neural network. Okay? And if you see any of the machine learning problem, any learning problem, one of the most important part in the learning model is something like representing the samples that you are going to use. Suppose I have talked about, say, image classification in the previous slide, right? So as such, your algorithm cannot take, say, a human as the input, right? You are going to take as an image or some sort of inputs. So first of all, how do you represent those samples so that you can apply any learning model, statistical model, or any other models? So you have also seen something like ARIMA, right? So in ARIMA models or ARIMA models also, like say, you may have a sequence of inputs. So if your so in the model, what you see is some kind of numerical values of some vector, right? But when you apply to the real world problem, samples need to be first represented in some form which can be accepted by the models, right? So you take up a machine learning model like classification, clustering, or regression, or some statistical models. First, you need to have some sort of representation. So neural network can be used to generate representation of the samples. So this is say representation. Right. So likewise, again, any other estimates like probability. Okay, I want to estimate something like given a particular some event E1, I want to predict some event E2. Some estimate. I'm just taking one example. So I want to estimate some function. Okay. So for performing estimate, also you can use neural network. So what I'm trying to say is that most of the real world problem that we are facing, starting from the representation learning to estimate to classification to regression, okay, you can use neural network. So the same model that you are going to use, the same model, okay, can be defined in different form based on what you need. Okay? So the output is going to be different depending on whether you are going to perform regression problem or classification problem or representation problem or estimates, right? That will be different, but underlying model can be used for the same underlying model can be used for different types of problems. Okay? So this is the advantage and beauty of neural network. Okay? So so with this brief say introduction, okay, let us see what is the how a neural network looks like. Okay? So you might have those who are new to the field, okay, but you might have seen when it talks about neural network, you see a network of this kind. Okay, you have something called input layer, something called output layer, and something called hidden layer. So depending on the underlying problem, okay, I am going to play with how the say this output layer will look like. If I want to perform a regression, I may have the design of my output layer might be different. Okay, if I want to do a classification problem, the design of the output layer is may be different. But in general, when you say a neural network, very basic neural network, it may look like something like this. So this particular neural network, we generally call it as the multi-layer perceptron. So let me know if there is any questions. Please feel free to stop me. So this type of neural network you generally see in the very basic and say introductory courses of neural network. This is called multilayer perceptron. And let us try to understand what is this network and how this network works. Okay? Because this is the basic building block for any other neural network that we are going to discuss, or any other neural network that we are going to use. So let me go back one more slide. So before I start further discuss, let me first mention that there are broadly there are 3 different types of basic neural network models, and these 3 and all other advanced form of neural network are some kind of constructed using these 3 neural networks. One is, as I have just mentioned, this is called multilayer perceptron. Then next model is something called recurrent neural network, RNN. And this is what we are going to look at, recurrent neural network and its variant. This is what we are going to look at. Okay, this is basically for sequential problem. Okay. But if you look at the RNN model, it's a kind of another variant of the multi-layer perceptron, okay, with the time propagation. Then another basic component is called CNN, convolutional neural network, okay, which is basically applied for large dimensional samples, which will allow you to reduce the number of parameters and so on. So these are the 3 basic components of neural networks, and most of the advanced neural networks are some combinations of these 3. Okay? So with this, I was talking about this basic multilayer perceptron, but what we need to know is what are these circles and what are these connections. So neural network, when you see like this diagram, this is a kind of conceptual representation of the network. But as such, when you actually implement and try to understand how neural network computes and learns and works, right? So this is all about linear algebra, okay, say matrix algebra. But pictorially, for high-level understanding, we are looking at something like this network. So when you see this network, there are 2 things. One is the connections, and another is this circle. So these circles are the basic computational units, okay, which consists of 2 components inside. Okay, so if you try to zoom any of these this circle, okay, there are 2 parts. One is called perceptron part, another is the activation function. So what is this perceptron? Okay. So this perceptron is nothing but it is trying to combine the say input information coming from each of the connections. Okay. So if you see that you are going to have for each of this network, you have these circles, and in these circles you have incoming connections, right? And each of these connections will be having some weights. Let me call it something like W11, say W12, and so on. There will be some weights. Okay? This is what I am defining here. So there are some weights for all these connections. And in these circles, first thing is that you combine all the incoming connections. So that means you are going to combine means you are going to perform sum of all these incoming connections. That means if you have this weight V something like ij, let us say when I is equal to 1, j is equal to 1, this corresponds to V11. And so this connection, V11 is the weight of these connections, and this node, okay, it is producing some output. Okay? So some information from here it will be passing. Let me call this as the H1. Okay? So the weight, the perceptron part of this node is nothing but the incoming information, which is nothing but HI, into the weights that you have. And you do this for all for this particular connection, you do this for all the incoming links. Okay, that means you are going to have say I is equal to 1, 2. Let us say I have X number of these nodes. Okay. So input connection from here, 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 and perform some of this. Okay. This is what I'm going to get here as the say, let me call this as the O1 something. So the first component of this node is the perceptron, which is represented by this part of the nodes. So output from this perceptron, okay, this is again passed to another function called activation function. Okay, so this is the activation function, second part. So activation function F is will take the output of this perceptron. Let me call it as something like 0, 1 in the previous case, and this is what will be produced as output from these nodes. Okay. Output from these nodes. So every nodes in this network consists of say the perceptron part and activation part. Okay. And the output of the activation function is the output of these nodes. Okay, so irrespective of it is the node is in the input layer or hidden layer or output layer. Okay? Every node will consist of perceptron and the activation function. So what is the activation function? What it tries to do, right? So if you look at the perceptron values might be any real numbers, any negative number or the negative value or any positive values. So it is a kind of unbounded values. So you want to say apply some bound on that, okay? So just to have a very high level understanding of it. So perceptron will restrict the value between certain range. Let us say -1 to +1 or 0 to +1 or 0 to infinity and so on. It wants to restrict the output values so that it can bias towards the target task. Suppose if I'm doing for some classification tasks like human and vehicles, and if I say that say human represents the -1 and the vehicle represents the +1 and so on, then maybe that I will apply some appropriate activation function that will produce the value between -1 to +1 or something. Okay, so this is what the activation function, and this is and you have weights to all the connections. So main two components that you need to understand here is in neural network, basic neural network is activation functions. Which activation function you need to use, and how do you get the values of these weights, okay, associated with each of the connections. So these are some of the activation function that are used in the literature. Okay? Like sigmoid, linear, then some hyperbolic tangent, ReLU, and so on. There are people have tried different types of activation function depending on the underlying task. So, so if you are using say any neural models, okay, you have to use one of these activation function depending on the underlying task. And the plots that you are seeing here, red plots, is the kind of output values for each of these activation functions. So with this basic understanding, let us try to build a very basic neural models for performing very simple operations. So generally, these examples are the kind of very traditional examples that we generally take to explain about the neural networks. So first, yeah, please.
Sir, I have one question.
Yes.
How we can decide which activation function we will use?
So that depends on the underlying task, okay? And we will look at, we'll try to understand that as we go along, okay? But at this point, let us not worry about that. But the choice of activation function is important, okay? But we'll come to that.
Okay, and second one is why activation function is needed.
So sometimes, so if your values are not controlled, okay, then you may not be able to get a kind of stable model. Okay, so we want to say an advantage of activation function is that you are kind of normalizing the output of these say nodes. By doing so, you are also reducing the variations in the outputs as well as some sort of noise as well. Let us say one node is giving something like 1,000, some say 1,000. Another node is giving something like say 800, for example. So in terms of scaling value, right? It is so the influence of that might be, the effect of that might also be very high. And again, that is primarily the effect of the unnormalized values. At the same time, what are we looking at, right? So if I am looking at some values, say in the classification problem, if I am looking at something like say binary classifier that I have just talked about, two class problems, human and vehicles. If I represent that minus one is human and the plus one is say vehicles, then somehow if I can probably produce some bias output from these nodes towards either the human or vehicle, towards a minus one or plus one, okay, then that might say that might be more effective than the raw values. So if you look at this activation function here, let us take one example, say hyperbolic tangent. Okay? If you see that only the small part of this, the small part of the input values which is close to zero, okay, you have the some kind of wide range, but after that it is converts either towards the plus one or minus one. Okay? Or if you look at the say sigmoid function logistic, okay, it is from 0 to plus 1. If I say that my negative is 0 and positive is 1, then all the values, it will try to produce some bias output towards. So that means in every step you are performing some discriminative say decision process, right? So that is also another one. So one is that it regularizes the outputs that will reduce the kind of help in stabilizing the models. At the same time, it is also producing some bias outputs. But it all depends on which activation function that you will be appropriate for your model, right? That is going to depend on the underlying problem. The choice of that we discuss after having certain level of understanding. Have I answered your question?
Yes, sir.
Yeah. So I was trying to explain these two examples. So I have taken three basic examples. So this is these two examples. First one is for performing N gates. Okay? I'm designing a neural network for computing a Boolean N operation. Right? You all know what is N operation, right? This is a truth table. If I perform N operation between 0 to 0, output is 0. 1 to 0 is output is 0. 1 to 1 is 1, and so on. Likewise for NOT gates. Okay? Similarly, you can design for OR gate and so on. But if you see this neural network, two things I want to bring to your notice. One is that this blue node is the output layer. Okay, and these white nodes are the input layer. So how do you decide the number of nodes in the input layer and the number of nodes in the output layer? So it all depends on the underlying problem. Okay, well, how many inputs you are having, how many output units, right? So in the AND gate, it is the Boolean or the binary operator. So you need to have two number of inputs, and it is going to produce a single output. So you have only the one output. But in this example, I don't have any hidden layer. Okay. So number of hidden layer is 0. That means hidden layer is something that needs based on the underlying problem. So you in your network model you may have no hidden layer, one hidden layer, and more hidden layer. So likewise, in the case of NOT gate, you have only one input and one output, no hidden layer. Then what are the values that I have assigned to each of these connection? So in the connection, I have assigned 1, 1, and I have assigned something like 1.5 as a threshold. Okay? So how it works is, this function basically means that if the output of the perceptron, okay, the perceptron here is input 1 into 1 plus input 2 into 1, right? This is the perceptron part. Okay? So this is the perceptron. If this value is greater than 1.5, then you are producing 1, else you are producing 0. Okay? This is the meaning of this diagram. So it's telling that, so this box is, so you are the input Boolean values into weight 1, and the sum of all these connections is what the perceptron is. If this perceptron value is greater than 1.5, then I am returning 1, otherwise I am returning 0. Okay, so this if else function, okay, this is nothing but activation function. So this is a very root design of the this particular network. Okay. But why I'm explaining this is that, how do you know that, right? The weight of this connection should be 1. Okay. I can solve the same problem with different weights. Even if I do that, okay, if I assign instead of 1, if I assign some other weights, and if I change the threshold value, then also similar output I may be able to produce. Okay, so a neural network you may design manually if you know what are the appropriate values. Given the real world problem, you know that the network should look like something like this, and these are the appropriate values. If you can manually work out and produce, okay, I can also design this neural network manually. Okay? Neural network is nothing but this kind of connections, right? So the example that I'm showing here is I have like the weights are manually work out and the fixed. Okay, so this is how these networks are designed. Okay. Likewise, another example is for the XOR gates, and here you have one output layer, one node in the output layer, 2 nodes in the input layer, and you have got one hidden layer. Okay. So for some problem, okay, it is not sufficient to solve the problem with only input layer and output layer. Okay, so some problem may need some intermediate representations. Okay, in such a case, you may need to have a hidden layer. So one example is the XOR gate. You cannot write XOR. You cannot develop a neural network for solving XOR gate without the hidden layer by the nature of the problems. So likewise, so whether you will have a hidden layer or how many hidden layer you may need may also depends on the nature of the problem. And the hidden layer basically try to generate the intermediate representation of your inputs. So the more you have the more you have the hidden layer, maybe that you may be able to represent the input layer in the more detailed manner. Okay? So likewise, so when you say deep neural network, what do I mean by deep neural network is generally deep refers to how many hidden layers that you have. If you have lots of hidden layers, okay, then your network is considered to be diff. Okay? So diff neural network is nothing but the same neural network with kind of multiple hidden layers. Okay? So, but here in this example, what I'm trying to say is that you can design the network, you can manually work out the weights, you can manually work out the activation functions, okay, and come up with a neural network. There is no problem if you know the problems, right? But what is the general say difficulty? So many of the say real world problem, it is not clear, right? What what is the characteristic? You may not have the complete picture, right? Then how do you find? How do you determine these weights? How do you determine these weights, right? So that is the problem. So learning a model or learning a neural model basically means how do you learn these weights? Instead of fixing manually, now I want to learn. Okay? So then how do you learn? For learning a neural network or any other machine learning models, you need to have something called a training data sets. Okay? So I am going to assume that I have a training data set, and from these training data sets, I am going to learn these parameters. Okay, so something like suppose the classifier I have talked about, right? So if I give so I will my example. So I will assume that I have some training data sets. My training data set looks like something like this. Suppose if you have a samples. Let me call it as the D1 first samples, and what is the corresponding output? Okay, let me say this is the human, and D2 is vehicle, D3 is human, and so on. These are the levels. Okay? So that I'm going to assume that I have some set of this level data, okay, that will allow me to learn my parameters. So when I assume this, what are these? What is the meaning of this? So DI, D1, D2, D3, these are the inputs. Okay? Inputs. These are the outputs. Okay. That means in my neural network models, my inputs are. So if you look at here, so my inputs are these nodes. And in the output also, I have two nodes, right? So, but in my samples, D1 belongs to head, human, D2 is vehicle, and so on. If this is my samples, how do I fit these samples in a class level into my model, right? So I have to transform this particular, these samples into some form which is accepted by my model, right? And I have to transform the output, which is human and a vehicle, to some representation that can be produced by the model. That is what we need to understand. So let us see what kind of input a neural network will take. So in this particular example, what are the inputs here? If you look at this inputs are nothing but a vector. Okay? I'm going to, in my neural network will understand only the vector as the input, this particular neural network, okay? So if you see this diagram, so X1, X2, X3 is, let us say this is the first sample of D1, representation of D1, which is represented by a vector, X1, X2, X3. Vector means I'm going to have some real number here. Let us say this, so somehow using some method, I have transformed this D1 into something like a vector of something like say 2, 1, let us say 0.5 or something. So I transform my sample into some vector. Okay, this vector is what I'm going to give as input to my neural network. This will be 2 will be given here, 1 will be given here, 0.5 will be given here. Then how many nodes you will need in the hidden input layer depends on what is the dimension of your vector. If your vector is having dimension k, that means you are having k number of nodes in the input layer. Okay. Likewise, how many output nodes you need in the output layer, depending on if I assume that okay, I have vectors, okay, and I will assume that if I get something like 1, 0, this means human. If I assume that 0, 1 basically means is the vehicle. If I assume this way, okay, then I can probably I need to nodes in my output layer. So if you see here, the output layer is also a vector, right? The output from the output layer is also a vector. So you are giving a vector as input and you are producing a vector as output, okay? And depending on the nature of the problem, your vector size may be, output vector size may be different. It may be 1, it may be 2, it may be 3, depending on the problem. So, so this is how input and the output of a neural network will be realized. And then, what about the hidden layer? Okay. Hidden layer is a kind of user parameters. User has to decide how many input layer you need. Okay. So, if you are say in this example, your number of nodes in the input layer is larger than the hidden layer is larger than the input layer. That means you are projecting your. That means, see, in this input hidden layer also, it is also producing another vector. Okay, and the dimension of this vector is larger than the input vector. So this is like you're projecting to the higher dimension. If you have a smaller number of nodes in the hidden layer, that is like you're reducing the dimension. Okay? So depending on the needs of the problem, user can decide how many nodes you are going to put in the hidden layer. Okay. So this is about the hidden layer. Again, if you see here, the output of hidden layer, okay, this is another intermediate representation of G1. Okay? So that means you can use hidden layer, output of your hidden layer as the representation of your input vector for some other problem also. Okay? That is how we can use a neural network for representation as well.
Excuse me, sir. I just had a small question. May I go ahead?
Yeah, please.
Sir, if by increasing or changing the number of hidden layers, if it improves the accuracy of the prediction, say for example, then is it advisable to keep on increasing the number of hidden layer, or is there a limit to it?
So let us see the sparsity of the problem. Okay. So suppose you have a small data sets, small samples. Okay. And when you increase the number of hidden layer, the representation in the hidden layer, right? You are going to get a very because you have a huge search space now, right? Your dimension is large. You have a huge search space. Then if you increase very large and very few samples, right? Then your representation in the hidden layer is going to be very, very sparse, right? So whether the sparsity will help or not, it depends on the nature of the problem again, right? But generally, if you have a say small sample size, increasing the number of nodes may have negative influence as well. If you are projecting to much higher dimensions and your points are much is very sparse. Okay, so the traditional challenges of a machine learning problem in the sparse when you have a sparse data representation, similar problem you may arrive. So it's not really advisable to say extensively increase the number of the hidden layers, but how do again hidden layers are kind of user-defined parameters. So how do you decide a number of hidden layers here? Let us assume that I have a problem. Okay, let me try to draw in this one. Let me assume that I have a classification problem and they are not linearly separable, or say they are not separable in the lower dimension, right? One way of solving this problem is you project in the higher dimension. So the moment you project in higher dimension, you may be able to linearly separate them. Okay. So if you have a kind of non-linearly separable data sets, which is very likely going to happen in the most of the real world problem. So projecting in the higher dimension will help in separating them. So increasing the number of nodes in the hidden layer is like projecting in the higher dimension, where you may get better separation. Okay. Again, in other way, that your salience is not the whether they are linearly separable or not, but your salience is that it is a much sparse representation. Okay, then I want to have a more dense representation, which is really something like dimension reduction. In such kind of problem, representing the in the lower dimension may work. So it's all depend on the nature of the problems, nature of the data sets, and these are user parameters.
Sir, I have one question. Sir, like in multiple linear regression, do we need hidden layer? Because we can write the output in terms of like B1 x1 plus B2 x2 plus B3 x3. So there is no hidden layer required in the multiple regression.
Okay. Let us shall we delay the answer to that question a little bit, because what I need, okay, in the regression is that given a vector, okay, I want to produce one real number, right? So if you are having in the you need say single dimension, you have only one values. That means you have only one node in the this one, and you need another in the say another one node in the output layer. But when you give the vector, right? When you get the vector in the multidimensional linear regression, you are going to have say a vector as the input, and whether you will have a single output if you are looking for the single regression, or multiple output you're looking for multiple regressions. But what is the advantage of hidden layer? Advantage of, so irrespective of the nature of the problem, okay, and the advantage of hidden layer is that you will be able to project your input into multiple representations. Okay, so hidden layer, having a hidden layer is will help, because your input may not be able to say your input vector may not be appropriate, right? So you may have better representation by having a hidden layer. Even if, but problem is, that is what I'm going to discuss. Okay, let us first let us continue a little bit, and then let us come back to that. So now I have just talked about, so now whole our problem is, if I am not able to design the network by deciding the weights manually, then I have to learn these weights, and that is what the real world problem, and that is what the building the neural network models. And we are going to learn this from my training data sets. If my problem is a classification problem, I'm going to have, for every samples, I'm going to have the corresponding levels. If it is a regression problem, for every sample, I'm going to have some real number here, R1, R2, and so on. So this is what I need to have. Okay. So from this, I need to learn my learn these weights. Okay, that is what I want to explain first. So let us go to that, how neural network works and how the parameter learns. Let us assume that I have a network already. This is my network, okay? And I have decided some weights, initial weights. So the numbers in each of the connection that I'm giving here are the initial weights. Okay. Then, but these weights may not be proper. They may not be the appropriate weights, and that is what I want to learn from my training data sets. So I'm assuming that in my training data sets, I have D1 corresponding output. That is, in this example, my output is going to be something like a vector. Okay, let me call it as the output vector O1, and these are vectors D2, O2 or something. Okay? D3, O3, and so on. This is what I have. I'm assuming that. Okay, this is my training data set for building my model. And using this training data set, I'm going to learn the appropriate weights of this. Okay, so so I have to start from some initial weights of these connections. Okay? I'm assuming that these are my initial weights. Okay? So how the forward pass happen is, when I give the first example, let us say D1, okay, I'm giving D1 as the first example, which is represented by this vector, okay, 1, 0, 1, and so on. This is my input vectors. Then it will just move forward into this network. Okay, so I was talking about perceptron and activation functions. So generally, in input nodes in the input layer, there is only one input. So perceptron will produce the whatever is the input as output of the perceptron. And what about the activation function? Generally, for the input layer, activation function is linear. Linear means whatever you are receiving, you are producing that as the output. Okay, that basically means if I'm giving 1 here, this will be producing 1. Okay? If it is 0, it will be producing 0 and 1 and so on. So this is, so you are going to just get the output of this input layer is whatever input vector that you are having. So now it will move to the second hidden layer. So this is my input layers, and this is the output of this one. It will go to the hidden layer, and in each of the nodes in the hidden layer will be performing the perceptron. This is what we're going to do, right? The weights and the input 1, right? The weights of this input this one, and so on. This is what you are going to. These values are some random number I have given. So this perceptron I will be performing. Then I will be using some activation functions. And let us say I have considered sigmoid as activation function. And this will be produced from the output of this one. Okay? This will produce 0.668 and so on. So this is what I'm going to get. And this I need to do this for all the nodes in the hidden layer. And so this is just the likewise, and it is so this is the values for these are the output from hidden layer. And if you see here, this is also a vector. Hidden layer is again producing as a vector. Okay. So the output of hidden layer will be taken as the input to the next layer. The same thing, you apply the perceptron and an activation function, and output is producing another vector. So the flow of the input vector from the input layer to the subsequent hidden layers and to the output layer, this is called forward pass. Okay, so this is a very simple step. You perform the perceptron, activation function, and so on. You go up to the output layer. Okay, this is the output layer is producing one vector. So now question is, the output that you are getting, is it the output that you are expecting? Okay, if you are getting the output that you are expecting, that means what? The weights that you are having, they are appropriate. If you are not getting what you are expecting, that means the weights are not proper, there is an error. This is what I want to see. So that before that again, the whole computation that I have just done is a forward pass. We can realize this. We can realize this in the form of, say, algebra, because this diagram form is just the visual understanding, but what is happening inside is nothing but the matrix algebra. Let us see how it happens. So if you see here, what are these weights? Okay, the weights are nothing. This weight is nothing but the matrix. So the weights, the first weight between the input layer and the hidden layer, okay, this connection, you can realize this by a matrix. So I am calling this as the matrix W. Okay. What is this matrix W? If you have each of the rows, if you have three number of input nodes, I am having three rows, I1, I2, I3. If I have four number of nodes in the hidden layer, I am having four columns, H1, H2, H3, H4. Okay. So the connection from I1 to H1, which is this cell. Connection from I1 to H2, this is this cell. This is this cell. Okay, this is this cell. That means each row represents the output connection from a nodes, right? Likewise, second row represents the connection from the second nodes in the input layer. Likewise for this one. So in this manner, I can realize this as a matrix. So W is the matrix representing the weights in the weights between input layer and hidden layer. And what is the size of dimension of this matrix? This is 3 by 4 because I have 3 number of nodes in the input layer and 4 number of nodes in the output layer. Similarly, the next weight between the hidden layer and the output layer, this is also a matrix, the same way, right? I have 4 hidden layers, so I have 4 rows. I have 2 nodes in the output layer, so I have 2 columns, right? So likewise, so this is the V, this one. So if you, everything is about learning this two matrices, W and a V, if you have one hidden layer. Then if we say that, what is the parameters of this neural model? Okay. So when you say parameters are some those variables that are not provided by the users, right? So if I say how many parameters you have, parameters is nothing but this W matrix and a V matrix. Okay? And a W matrix and V matrix will depend on the dimension of your input, dimension of your output, and dimension of your hidden layer. Okay. So if my dimensions are very, very high, then your parameter is going to be very large. Okay. So that is also you have to see. Okay. But what I was trying to show here is when you perform that forward pass, how exactly what is going on in this matrix. Okay. And this is what exactly is going to happen when you implement the neural network. So if I just see the first first level input, okay, I'm giving this input vector, that this is my V1, okay, Vi. And when I give this from input layer to the hidden layer, if you see here, so I'm assuming that I already have some initial values in this matrix W and V, because I'm assuming that I have some initial values. Okay? Based on these initial values, I have some initial say W0. I have some initial W0. So what I want to show you is when you actually move from input layer to hidden layer, what is the internal estimates? Okay? So this is nothing but, so for finding the output of this hidden layer, okay, what is this? The perceptron, right? I want to do the product of this weight and the output of this weight and output, this weight and the output of this, and so on. I want to perform summation. This is nothing but, if you look at this one, the x1 into w11. That means you are multiplying this one with this one. You are multiplying this one and this one. You are multiplying this one and this one, okay, which is nothing but this p1, right? So likewise, what is h1? The value of p1 you apply to sigmoid function, you are going to get h1. This is what we're getting here, right? So this is nothing but the matrix, say vector and the matrix multiplication. Okay. So likewise for what about output for this? This is nothing but you are multiplying this one with this one, this one with this one, this is for the perceptron, and then sigmoid. Similarly, you are continuing this and doing it for all the nodes. So this is exactly the product between the X and the W, right? When you multiply X and W, right? What you're going to get is the output vector. Is PT, one is the output vectors. Then we apply the sigmoid in this one. So this forward pass from this layer to this layer is nothing but product of this X and the W, and they apply the sigmoid function. And this is what is going on inside this neural model. So similarly for the next layer is again the product of the output of the hidden layers and this matrix, V matrix, and produce the perceptron output vectors and apply sigmoid and then get the output is one. So this is what the forward pass. So you are first performing these matrix multiplications, vector and the matrix multiplications, and then get the hidden layer output. You repeat this for the say output layer and so on. So internally, even if visually it is a network, internally this is nothing but matrix algebra, and that this is how it is estimated. So with this understanding, we were talking about the errors, right? So now we know, given input vector, how are you getting the output vector? So now we have got the output vector. Now the question is this output the one that you are expecting, right? Because you already have your training data set. So in the training data set, you know that for this given input, I should be getting this output that you already have. So if you are getting the expected output, that means these parameters are correct. If you are not getting the expected outputs, that means these parameters are wrong, right? If these parameters are wrong, then you have to again recorrect these parameters. So this is what the loss function. So now you are having observed values and expecteds. This is just the demo. Let us say my expected is 0, 1, 0 vectors. And you are getting this, then I have got some error. Okay. So using this error, I need to now reconnect these initial weights of the matrices, and this is what this recorrection is called learning. So learning or building the neural model is nothing but finding the appropriate values of these parameters, and generally we use some gradient descent approach, and that is what we are going to just briefly explain. So now I have just illustrated one example, but okay, this is just one example. Okay, there are several error functions like mean square error, cross entropy loss function, and so on. But just for illustration, I am just taking a dummy error functions like E is the difference between Y and the Y prime modulo or something. But loss function, there is something that you need to take care when you use the loss function. Say loss function should be differentiable because you are going to use the gradient descent, so that will get later. So now you have got some error. Using this error, you need to recorrect these parameters. That is what the building or learning a neural model. And that is, we're going to do the gradient descent approach, and that is, we call it as the back propagation. So learning the parameters in the neural model is something called back propagation through time. Or say that is for the sequential or simple back propagation. So I'm going to use back propagation for learning the parameters. Okay. So how do I do that? Okay. So I'm just going to briefly explain how I'm going to do the back propagation. So now what I want to do, I want to correct these weights, right? Every connection, weight in every connection, I want to do the corrections. Okay. So as you know that in the optimization, how do we find the how we do the optimization, right? So given a loss function, which is E in this case, I need to take the partial derivatives of the loss function with respect to the parameter that I want to optimize. right, and assign to 0. This is exactly what we need to do here. So now, for correcting the first values, suppose if I want to correct this, what I need to do is partial derivatives of the E function with respect to, let us say this is V11. This is what I want to do. So this is what I'm trying to represent here and assign to 0, okay, and then get the assigned to 0, and then after that you try to find what is the, after assigning to 0 you solve this problem and then get what is the error, okay, or what is the gradient, right? So after getting this gradient, so you will need to update these values. So how are you going to update? So this is the new values, this is the previous values, this is the gradient that you have just estimated, and this is the learning rate. Okay? So learning rate is some small number. Okay? So likewise, we show by estimating these values, we are going to get a new value by estimating this expression. So likewise, you are going to do this for all the parameters that you have in all the connection you have in this. So this is for estimating these parameters. So how about estimating these parameters? For estimating this parameter, you repeat the same thing. Okay, you perform the partial derivatives of E with respect to W, find the gradients, and update the WI, these parameters. So this is what we call as the back propagation. Okay. So any question at this point? Yeah. So you do this back propagation for all the training samples. And so one cycle of this training sample is, we generally call is the epochs. So when you implement the neural models, you will quite often you will see encounter something called epochs. That is nothing but say with one cycle of the training samples are given into the models and readjusted. Then only one cycle may not be enough. Then you may need to repeat this epochs many times, okay, till your error is acceptable. So that is the back propagation. So with this, I would like to just give one more brief explanation about how to perform these partial derivatives. So let us go a bit. Okay, let me use just ignore the title. So I am trying to explain how to estimate that parameters. So I'm trying to redraw what we have just seen. Let us say this is my hidden layer, ice. This is ice1, ice2, ice3, ice4. And this is my output layer. And this is, you know that this is how it is connected. Right. So I'm calling this as the Y1. I'm calling this as the Y2. And as you know that you have something called perceptron here. Let me call output of the perceptron. Let me call it as the O1, O2. And I have error now. I have error. Error is some error functions. In this example, we have taken some, say, modulo of Y minus Y prime or something. So this could be any error, any appropriate error function. So, but what I want to calculate is V of 1, 1. So if you look at, so now what I want to do, I want to perform partial derivatives of E with respect to V11, right? This is what I want to find, estimate, right? But if you see here, E function, the E depends on Y. This is Y output, Y1, Y2, not on this V1 partial derivatives of V1, not on the V11 that I want to estimate. Then how do I do that, right? So now I cannot take partial derivatives of E because E is independent of V, right? So I have to apply chain rules and estimate the chain rule and make it appropriate dependence. So that is what I'm trying to see here. So E depends on Y. So let me call it as the partial derivatives of Y1, or say let me generalize it as the V, okay, matrix. So let me call it as the Y. Okay, Y is the vector now. I'm just generalizing for both the things. So I'm taking partial derivatives of E with respect to Y because E depends on Y, right? Then Y depends on O, output of this perceptron. Now O depends on V1, V. O depends on V. Now I can take the partial derivatives. So I have to apply the chain rules and to estimate the corresponding gradients. Okay. Likewise for the parameter W also. What I need is parameter E of W, and E does not depend on W. So I have to apply the chain rules to make it like derivable, right? So likewise you apply the chain rule. Okay? So something like E percentage of this Y into now Y depends on O and O depends on H. So O depends on H and H depends on W. Right. So likewise, you have to expand and perform the chain rule. So this estimate, so back propagation is nothing but, so in the back propagation, what we are doing is that take the partial derivatives, and so since it is not, say, error does not depends on the parameters that I want to estimate, apply the chain rules, okay, and estimate the intermediate these derivatives to estimate the corresponding gradients. Okay, this is what the back propagation, and this error rate is something like if you set the error rate very high, then your iteration will be very fast, but you probably may miss the best values, the optimal values. But if you you put the error rate very small, then you will find the appropriate values, but the number of iteration to convergence may be very high. Okay? So this is again trade-off which user need to define. Okay? If you set the error rate very high, you may not get the optimal values of the parameters. You may miss. And if you set the error rate very low, then you may not. Then you may get the optimal values, but you may miss. So this is what the multi-layer perceptron and how forward pass happens and how the parameters are estimated. So even if you have multiple hidden layers, okay, this is one input layer, hidden layer 1, hidden layer 2, output layers, okay, then you have one vector matrix, parameter matrix here, another parameter matrix here, another parameter matrix here. So having more number of hidden layer means you are going to have more number of parameters. So it all depends on that. So I think with this, let us come back to the question about a regression. Okay? So in your regression, your inputs is a vector now. Okay. Now, and you are going to have a single output y1, right, for the sample s1. So if I do not have this hidden layer, then what happens? I'm directly going to connect here. Okay, so let me draw somewhere here. So if I do not have hidden layers, from here you are only connecting this. Okay, and I just need to learn this vector w, because I have only one hidden layer, output layer, so this is a vector, right? So how well you will be able to learn this vector w, right? So generally, and you don't have much parameters here. So if you have a kind of much complex data set, you may not be able to learn the appropriate weight for the appropriate values with this vector. So it may be better if you have a hidden layer, which may be whatever it is. and you have something like this. So in the regression also, okay, this is your E1 regression vectors, and this is Y1. You are going to have scalar. So in the regression also, it is necessary to have the hidden layer, because you will be able to get more parameters and a better representation. So before I move to this, so this is the brief understanding of multi-layer perceptron. And before I move to sequential problem, and that is the focus of the next 2 days and the next discussion. Before I move to recurrent neural network, let us, if
So
I have questions.
yeah, so can you explain, sir, once again, what is epoch?
Okay, epoch is like, let us say you have one training, you have training data sets, and all the inputs to all the samples in the training data set you have already given to the model, and you have learned one cycle of the all the inputs, let us say. Okay? But what happened? Still, your parameter weights might not be appropriate. Okay, then you give the entire training data set again for the next time. So one cycle of the training data set, that is what epoch is.
So same training data set we have to give, or another data set, training data set?
Same training data set.
So then how the things will be different, because the equation, mathematical equations will remain same.
It's same. It's still same, but your weight will be weight can be different, because you. 1 second. Hello. Yes. Oh, all right. Yes. Regarding that project, right? So we are working on that, and in next 1 or 2 days we should be able to communicate. Yeah. It is starting soon, because it is already in the finance section. So yeah. So we're expecting starting this month. Yeah. So that is good. No. In the mighty. So sanction letter, yet to come, but based on their input, it's likely to start this month. Yes, because all the project staff, they have left because of this gap. We have to start all everything fresh. So since we don't have, since all the project staff left, we have to start again fresh. So so after that, after the last closing activities, we have not started any new crawling activities, but that will be starting soon. But we are also expecting your organization as the kind of users for giving feedback now. I think may not be required, because it is already like happening, and for participation we are already assuming that you are part of the team. So yeah. Yes. Thank you very much. I'm sorry that this guys is kept calling. Can you please tell me the questions again? Oh, epochs, right? So that is the epochs. So you are giving one cycles of the entire training data sets. But your question is that since the training data set is same, you'll be getting the same values, right? No, it is not going to happen. Because when you give the first input, okay, suppose you're training the data set something like this, D1, 2, and some DN, right? So when you give the D1 for the first epochs, okay, some changes will happen in the some adjustment will be happen in the parameters. Likewise, if you keep on changing, right? When you have the DN, you will have a new values of this W, right? W matrix when you give D1 for the second time. So D is going to keep on changing, right? So so you are going to get different values, but more converge towards the error. Okay.
Thank you, sir. Right. Another question, sir. Here is the O1 and O2 and Y1 and Y2. So this O1 is right a predicted one, and this Y1 is actual.
No, this is just the notation. So actual Y1 is the output from this node. Okay. So in this notation, as we said, you have two compartments, right? So I'm expecting that output from the perceptron is O1, OI. Okay, and output from this is YI. So YI is the output from, in this particular example, okay, YI is the output from the nodes, and OI is like output from the perceptron or something like that. But you please remember, every node here will have two outputs. One is from the perceptron, another is from the activation function. The output from the activation function is the output from the node itself, okay? But output from the perceptron is the intermediate output. But when you do the back propagation, you need to perform, because your error depends on Y. So let us just see. Error depends on Y, right? Y depends on what? Y depends on the O, right? O depends on V or H, right? So when you do the back propagation, you need to decompose at the level of perceptron output as well as the node output. That's why you need two outputs here. Can you see that?
Yes, sir. Thank you, sir. Thank you.
Okay. So if you do not have any questions here, let us go towards the recurrent neural network. So before I start recurrent neural network, let us try to understand what kind of problem the multi-layer perceptron can solve. Multi-layer perceptron, if you, as you just understood, you have a vector, input vector, and you have some output vector, right? So this is like you give one vector as input, and you get another vector. But what if, like say, you have already seen a regression problem? For the type of regression problem, there is something like sequential information in the input dataset itself, right? So you have input at the time T1, input at the time T2, and so on. Something like, say, if you have a time series data, or you have some dataset where you have some sequential dependency. Something like if you happen to know some NLP problem, like say, given a sentence, I want to classify this as a, say, some class 1 or class 2 or something like that. Then what happened? I can solve this problem in two ways. One is that entire sentence you represent as a vector, one single vector, and use the multi-layer perceptron to solve the problem. Another is, instead of the entire sentence, you consider the words in the sentence, and the sentence is given as the sequence of these words. Okay. So likewise, some sequential dependency in the data. So whenever you have something like a sequential pattern in the data, okay, then it is not that you cannot solve the problem with a multi-layer perceptron, but it might be more convincing or appropriate to consider some sequential model to solve a problem. So recurrent neural network is the basic sequential model in sequential neural model. There are various sequential models, but recurrent neural network is the most basic model. Okay. But whenever you have a sequential problem, it is recurrent neural network is applicable. Okay. But I can always force to use multi-layer perceptron also, the vector, what we have just discussed. So if I want to use multi-layer perceptron, the first thing that you need to do is the sequential information I need to transform into backward this vector representation, then I can apply multilayer perceptron. So I don't want to do the transformation to the backward this vector space models. I just want to capture the actual dependency sequential information in the input data. Then I can go with the sequential model. So recurrent neural network is one such model, and this is the most basic sequential model. How much time I have? Hello? Okay. So let me just briefly continue this. I probably have another 5 to 6 minutes. So what is recurrent neural network? Okay. The only difference between recurrent neural network and a multilayer perceptron that we have discussed, okay, is nothing but, so let us first see what is multilayer perceptron that we have discussed. In the multilayer perceptron, for simplicity, let me reduce the number of nodes in the hidden layer and assume this one. This is multilayer perceptron. Okay. So in the recurrent neural network, what are the changes? I'm going to have something like some input, something like this. The self loop or self this one. Or say I'm going to have something like this. So that means, what is the meaning of this? So now when you give the, so okay, this diagram is more meaningful. So this is the self loop. Okay, what is the meaning of this? So now, as I said, your input is going to be sequential: x1, x2, x3, and so on, right? So now, when you are going to start, if you start from the first input samples, okay, then give x1 into this model. Okay, when you are going to give this, then when you give the next input x2, what will happen is that you will take the output of this x1, output from the x1, also as the input to the next step. That means in the first instance, time instance x1, your input is only x1. Okay, in the second time stem, your inputs are x2 plus the output of the first node. Let me call this the hidden one, h1. Likewise, when you take the when you go to the third input, x3 is the input plus output of the second unit. So likewise, you are going to take the output of the previous units, okay, as well as the current input as input to the current model. Okay, so this is the kind of the temporal manner. This is what this diagram is showing. So at a particular instance t minus 1, okay, your inputs are this xt minus 1 and the output from the previous nodes. Okay? So these two will be taken as the input. Similarly, when you in the time instance t, this is the input plus this is the input. Okay? Likewise, this one. So you are considering the previous say output of the previous unit, okay, also for the model. Okay, so this is what the recurrent neural network, and this is this figure summarizes the process there. Okay, so that means you are having a self loop. Okay, so you are going to have say when you take this input, right, this input in the perceptron, you are also going to consider the output of the previous one. Okay, so this connection represents the output of the previous output. So likewise, so you are going to have the previous outputs and take as the inputs. Okay. Then you can, if you have a dense connection, this may also give as input to this one. This may also give input to this one. depending on the nature of the connections. So recurrent neural network is nothing. It's the multi-layer perceptron itself, but now you are also taking the output of the previous hidden layer. Okay? Output of the hidden layer in the previous input. Okay? That also will be taken as the input. Okay, so that is the only difference between recurrent neural network and a multi-layer perceptron. But by changing, having this extra connection, you are able to capture the contextual information, like previous input you are able to capture. So what are the parameters here? If you do not have this self loop, your parameters are only W and a V, right? Now you're going to have another matrix U. U represents the weight in this self loop, or weight in this feedback. Okay? So V will correspond to this one, this connection, and so on. So you are going to have one extra parameters in the case of recurrent neural network. So in the multi-layer perceptron, your output, if you remember the previous multi-layer perceptron, inside the activation function, what I was having, XW, right? Or say WX. I was having WX as the input, right? This is what this is something like SI. So this was what you have seen in the multi-layer perceptron. So in the recurrent neural network, only difference is WX, and this is time t. Okay, depends because it is now it is sequential. At time t, WX t plus U S of t minus 1, output of the hidden layer of the previous input, right? This is what we are going to have as the S of S at time t. This is the only change. So this change will so this second term will allow you to say capture the sequential information. Okay, now I think it is 1 o'clock. So today we'll stop here. So why I was giving special emphasis on this derivation is that when you go to the next more advanced model, without explaining the internal functionality, we should be able to understand. That is the idea. So now the same back propagation also will happen here. So tomorrow we will start with how to perform parameter estimation of the recurrent network briefly. Then what are the different variations of recurrent neural networks and what are the other state-of-the-art sequential models. Okay. So with this, I will stop here for today. And if you have any questions, you can have.
One question, is the neuron and perceptron the same thing?
Neural
Neuron and perceptron are the same thing?
Okay. The concept of neural network, okay, it starts from our brain. If you look at the brain, I'm not expert in this medical term, so this one, but if you try to understand our brain consists of something like neurons and the synaptics, snaps or something. So neurons are the computing processors, which is denoted by those nodes in the neural network. Okay? And the synaptics are the connection between these neurons. So in the brains, maybe we have billions of such neurons and they're connected by synaptics, right? So neuron is nothing but that biological terms of this neural network is inspired from the human neural brain system brain. where you have neurons and synaptics. That is the thing. But perceptron is trying to mimic how information is processed within a neuron.
So, sir, each node in the hidden layer is a perceptron, or the whole hidden layer is perceptron?
No, it's not about hidden layer. All the nodes in the network is will be having perceptron. Okay, so as I was explaining, in a node, whether irrespective of whether it is the input layer or hidden layer or output layer, every node will have some two compartments. So what is the first compartment? First compartment will do kind aggregation of all the input informations, right?
Yes, that's clear.
Weighted summation. So that weighted summation is what we call as the perceptron.
Sir, after you are inputting two layers, okay. So finally, whatever the output you are getting based on the function, activation function, that is perceptron, what I think.
No. Perceptron, generally this is terminology. So if you look at this one, say how this node is divided, okay, we will refer to that first estimation part as the perceptron, and the output of perceptron is given as the input to the activation function. Okay? That is how generally it is referred.
I think it is artificial neural network. Perceptron is access.
That's the simple.
Any more questions? Some people have asked some questions in the chat box. If you want, then you can repeat those questions. So if you have a question, please, instead of typing in the chat box, can you please unmute and spell out the question. Vivek Sharma, do you have any questions?
Yes, sir. Good afternoon, sir. Good afternoon, sir. Can you hear my voice?
Yes.
Yeah, I had a question. I have also typed it that if I have, say, an ideal input and some approximated outputs, can I fit them linearly so that I get that ideal output?
Your audio is a bit distorted. Can you repeat again?
Okay. Can you hear my voice now?
Yeah, it seems to be better.
Okay. So I have an ideal output, say a DFT plot, discrete Fourier transform plot, and I have some approximations to that output. Okay, I have say 10 approximations to that output. These outputs are DFT plots of certain other constructions. Now, can I approximate my ideal output with this approximations using regression or classification?
I am not actually getting.
Okay.
But what I understood is, you have some estimates.
Yeah.
Then you are applying some approximation there.
Yeah.
And you are telling that can you mimic that using neural network? Is that your?
Yeah. And what should I be using? Classification or regression?
Okay. So what is a classification? What is a regression? Let us try to understand.
Okay.
So in the case of regression, so classification or regression, you can probably define by a function. Okay. So f is a function that will produce some output. So if the output of this f function, if it is a discrete value, like yes, no, 0, 1, or say class level C1, C2, C3 or something, discrete values, then such kind of problems are known as the classification problem, where these class levels are already defined, okay, in the training data set. If the output value is a real number, okay, then we call it as a regression problem. So that is the very high level difference between a classifier and a regression. So in your problem, if your optimizer output is a real number, okay, it is like a don't say this is a regression, but it is like a estimation. Okay? So in the regression, what happened? You are assuming that you have a sequence of data or something, right? Or you have a vector or something. So if depending on your nature, okay, it can be a regression problem or it can be just estimates like probability estimate or some other estimate. So if it is an estimate, then it is if your output is a kind of real number, this is like estimating some function, producing some real number. But your output is a discrete values, predefined discrete values, yes, no, 0, 1, C1, C2, C3, and so on. That is the classification problem.
Okay. Okay, sir, I got it. Thank you, sir.
So, but again, as I said in the beginning, the beauty of the neural network is you can use this for regression tasks, classification tasks, representation tasks, and estimate tasks. Okay. For estimating some probability, estimating some function, I can use. Okay. So that is the beauty of the neural network.
Thank you, sir. I got it. Thank you.
Good afternoon, sir.
Yeah.
Sir, my question is: in case we propose a regression model using neural network, so how can that be helpful in predicting the future values? Because without having the future output values, we would not be able to predict the future output values.
Okay, I think question to this will be more clear tomorrow because I'm going to show that using this recurrent neural network. But just to give a high-level understanding, okay, let us assume that I want to predict the say this some like vehicle price in the next year, okay, and but I already have some previous year's data. Okay. So from the previous year data, I can generate lots of sequential samples. Okay. So, but regression is a supervised data, a supervised problem. Okay. So you need to have this training data set. So what is a training data set? If I want to do this prediction, my training data set is also going to be a collection of such sequential information. Okay. I'm assuming that I have this sequential collection of sequential information. Using that sequential information, I'm going to train my models. Okay. And once I train this, when I get a new sequence of informations, I can predict. But you need to have a training data set because this is a supervised approach. Okay. That means you need to have a collection of sequential data.
That can be done using sequential data set, right?
Yeah.
So solely with the help of a regression model, that cannot be achieved, right?
No. So regression model is one statistical approach. So I can also build neural models, something like recurrent neural network. We have exactly like a regression model. So in a traditional regression model, you do the curve fitting, right? So now that is the kind of some statistical method and optimizing the parameters. So I can also build a similar model with the say neural models, sequential neural model like RNN.
Okay, sir. Okay, sir. Thank you.
For building it, so that I would like to show tomorrow, but you can build.
I think that would be more clear in the next session. Thanks a lot, sir.
Yeah, welcome. But regression and neural network, okay, they are different. Regression is one another methods, machine learning methods. Neural network is another model, and neural network can be used to mimic what you do in the neural regression. Means you can build a neural network to perform a regression task.
Yes. Okay. Thanks a lot, sir.
Mm-hmm.
Okay, so if we don't have any more questions, then we can end the session here. Thank you, Ranbir. So
yeah,
thanks a lot. So you'll continue again tomorrow more. So your first